In particle physics, we can't observe particles directly. Instead, we study how they interact with matter as they pass through detectors. In this video, I will be talking about charged particle tracking detectors, which are used to reconstruct the paths of charged particles. I'll be focusing on one specific example, cloud chambers. I'll explain how it works, what historical implications it had, and how it demonstrates the same physical principles used in modern experiments today. When charged particles move through a detector, they interact electromagnetically with the material they pass through. These interactions leave behind a trail of signals that can be recorded and used to reconstruct the particle's trajectory. Tracking detectors are important because they allow us to determine key properties such as the particle's charge, momentum, and direction of motion. These detectors make up the innermost layers of modern experiments such as ATLAS and CMS and are essential for turning collisions into meaningful physics. The key physical process behind charged particle tracking is ionization. As a charged particle passes through a medium, it ionizes atoms along its path by knocking electrons free, and this creates detectable signals. By recording many of these interactions, often called hits, we can reconstruct the particle's full trajectory. Tracking detectors are usually placed inside a strong magnetic field. In this field, a charged particle follows a curved path due to the Lorentz force. Curvature, which is specifically the radius of the curvature, allows us to measure the particle's momentum, while the direction of the curvature tells us the sign of its charge. High momentum particles curve very little, while low momentum particles bend more strongly. In practice, the momentum is proportional to the radius of curvature, so measuring the radius gives a direct measurement of the momentum. To understand how charged particle tracking detectors work, it helps to look at a simplified picture, like the one I've got on screen. The horizontal lines represent layers of the tracking detector. So as a charged particle passes through each layer, it ionizes the detector material and produces a measurable signal, or what's called a hit. Each of these hits gives us position measurement, and then we can combine all of the hits or position measurements across multiple detector layers and reconstruct the particle's trajectory. This is shown in the diagram as the curved line. The crosses are the hits. These detectors are usually placed inside a strong magnetic field, which in this diagram is pointing into the page which is shown by the crosses. When a charged particle moves through a magnetic field, it experiences a force, which is called the Lorentz force, and that acts perpendicular to both the particle's velocity and the magnetic field. So in this diagram, it would be perpendicular to the curve. At the bottom, the Lorentz force is given by F equals qv cross b, where q is the particle's charge, v is its velocity, and b is the magnetic field. Because this force is always perpendicular to the particle's motion, it causes the particle to follow a curved path rather than slowing it down. The direction of the force on the particle can also be understood using Fleming's left-hand rule, which gives the direction of force for a current or moving charge in a magnetic field. So Fleming's left-hand rule, I've got the sign. Thumb is force or direction of motion, and then first finger is field, and then current is second finger. So if you line up your fingers with either one of the two, you can find the direction of the third. This explains why particles with opposite charge curve in opposite directions to each other in the detector. In most modern tracking detectors, the signals are recorded electronically, and the paths are reconstructed using computer algorithms. Examples of this include silicon pixel detectors and drift chambers. These both provide extremely high spatial resolution. Cloud chambers are unique because the particle tracks are directly visible to the eye, which makes them very intuitive ways to understand the basic principles of charged particle tracking. A cloud chamber, also known as a Wilson chamber, is a detector that visualizes the paths of ionizing radiation. It consists of a sealed environment containing a supersaturated vapor. This is usually alcohol or water, and this vapor is in a metastable state. So this means it is unstable and will condense very quickly once the thermodynamic barrier is overcome by nucleation. When a charged particle passes through the chamber, it ionizes the vapor along its path. These ions act as nucleation centers, causing tiny droplets to condense around them. As a result, a visible line of droplets forms, and this traces the particle's trajectory through the chamber. Without ionization, the vapor would remain transparent, So the track only appears because the particle locally triggers condensation, turning an invisible particle into something that we can directly observe. The cloud chamber was invented in 1911 by Charles Thomas Rees Wilson. Wilson was originally studying cloud formation and meteorological phenomenon, inspired by his work on Ben Nevis. He discovered that ions could act as sensors for droplet formation, which then led to the development of the cloud chamber as a particle detector. He was awarded the Nobel Prize for this in physics in 1927. Later, in 1936, Alexander Langsdorff developed the diffusion cloud chamber, which allowed continuous operation without the need for a repeated expansion. Cloud chamber tracks contain a surprising amount of information. As mentioned, the shape of a track shows the particle's direction of motion. The thickness of a track is related to how strongly the particle ionizes the medium. Heavily ionizing particles, such as alpha particles, tend to produce short, thick tracks, while high-energy cosmic ray muons typically produce long, thin tracks. So the more ionizing the particle, the thicker the track. And again, when cloud chambers are placed in a magnetic field, the curvature of the track can be used to determine the particle's charge and momentum. Cloud chambers played a central role in several major discoveries in particle physics. One of the most important of these was the discovery of the positron in 1932 by Carl Anderson. Using a cloud chamber placed in a magnetic field, Anderson observed a particle with the same mass as an electron, but with opposite curvature. This was the first direct experimental evidence of antimatter, and it confirmed a fundamental prediction of relativistic quantum theory. Although cloud chambers are no longer used in modern collider experiments, they remain extremely important conceptually. They were the first detectors to visualize charged particle tracks, and they laid the foundation for the development of modern tracking technologies. The same underlying physics, so ionization, magnetic curvature, and trajectory reconstruction, is still used today, just with a lot more sophisticated instrumentation. Charged particle tracking detectors are a fundamental part of experimental particle physics. By converting invisible particle paths into measurable trajectories, they allow us to determine fundamental properties such as charge, momentum, and to discover new particles.